This is the physics class. Today's topic is refraction through lenses. We have already looked at what refraction is as the bending of a light ray as it passes the boundary between two media of different densities. In this instance, we're looking at a different media, glass. What type of glass? A lens. We say when a light ray passes through a glass object or an optical media called a glass, it gets refracted. Means that what? There is a bending. Now this is a lens. We have different types of lenses. We have a convex lens. Convex lens. We also have concave lenses. What's the difference between the two? We had already looked at what concave and convex mirrors are. We know that one converges rays of light, the other diverges rays of light. In the instance of a concave and convex lens, the reverse is the process. I don't know. This is a concave lens. This is how it looks. A concave lens diverges rays of light. What does that mean? When light rays pass through it, they get what? They spread out. A convex lens, on the other hand, looks like this. A convex lens converges rays of light. It means that when rays of light pass through it, they converge, they meet at a point. So what's the difference again? A concave lens diverges rays of light. When the rays of light pass through the concave lens, they get what? Diverge, they spread out. For the convex lens, when the light rays pass through it, they do what? They converge at a point. At the point of coincidence or convergence is the point where the images will be formed on the lens. Recall what we did for mirrors. For a concave mirror, depending on the position of the object, you have different positions of the image. For a convex mirror, for each position of the object, you have the same characteristics of the image formed. In this instance, when you have a concave lens, wherever you put the object, you will get the same position of the image. So we are going to be looking at the characteristics of the images formed by the concave lens. But before then, what are the parameters of the lens? The different parts of the lens. Let us look at those parameters. It will help us to be able to construct those images. Okay, so this point here, I will call it O, is the optical center. This is the optical center of the lens. This is the point where rays are going to pass. Then, this, as usual, is the principal axis. Remember, the principal axis is also a lens. That is the major lens that passes through the optical instrument. So from there, all other rays are going to either converge or diverge. Equidistant from there, on either side, since the lens is a transparent medium, you can take the image characteristics on either side. You have the principal focus, and then you have 2 times the principal focus. So for instance, if I want to drop an object at this point on the lens, the light from the object is going to pass through the lens and the image will appear on the other side. The image can be at any point. It could be here, it could be at the principal focus, it could be here, it could be 2 times the principal focus, it could be behind or beyond the principal focus. What are those rules that will guide you in constructing these images, because you have to follow specific rules just as we did for the mirror, so that you are able to get the right position of the image, the right nature of the image, and then the image distance from the lens as well. Rule number 1, a ray must come from the object. Supposing we drop the object here, a ray will come from the object, pass through the optical center. Remember, when you are drawing ray diagrams, you must indicate with arrows. Those arrows show the direction of travel of the rays. Once it passes through the optical center, it is going to go back undeviated. Undeviated means that what? It's not changing its direction. It's not changing its direction. Let me do this. So it goes undeviated through the lens, comes out. The second rule says that a ray will come from the object, pass through the principal focus. Now, we'll see that the point where these two rays meet, the point where these two rays meet is the point where you have the image formed. If you trace this and then you join it and these two rays meet, you can see one of the rays coming from the object. This is the object. Supposing Mr. Amos is standing here, he becomes the object in front of the lens. The ray of light will pass from his head, pass through the optical center of the lens, and come this way, undeviated. Undeviated means that it's not changing its direction. It goes back through the optical center. Then the second ray comes from the object as well. Remember, you as an object, light is coming from you, is passing through the optical medium. It could be a mirror, it could be a lens, it could be a prism, whatever it is. In this instance, we're looking at the lens. So the second ray comes from the object, passes through the lens. When it does that, it gets what? Deviated. Initially, it's supposed to go this way, but instead of going straight across, it bends. That is the refraction. It bends and then passes. As a rule, it must pass through the principal focus, F. When it passes through the principal focus, it goes down. There will be a point of intersection of the two rays. The point where both rays intersect is where the image is formed. So, these are the characteristics of the image. This is the image here. This is the point where the image is formed. Can we look at the characteristics of the image? 1, the image is inverted. 2, the image is formed beyond 2F, that's twice the principal focus. Now let's look at the size of the image. Inverted tells us about the nature. The nature is that it is inverted. It is upside down. It is formed beyond 2F, shows us the distance from the lens where the image is formed. And then we have the size. What is the size of the image? You observe that the image is magnified. Some people will say enlarged. You observe that it's almost twice the size of the object. So these are the guiding rules. Rule number 1, a ray must come from the object, pass through the optical center of the lens to the other side of the lens. The second rule is that the ray must come from the object, pass through the lens, deviate through the principal focus. The point where these two rays meet is where the object will be formed. So I would like you to try it at home. What are all the other object distances? You can place the object between F and the pole of the lens. You can place the object between 2F and F. You can place it at F, and then you investigate the characteristics of the image formed. Again, for the concave lens, whatever position you place the object, the image characteristics will be the same. For the convex lens, depends on where you place the object. You are going to get different characteristics of the image. Is it clear? So we'll go on from there. We are looking at the lens formula. The lens formula is the same as what we had for the mirror formula, because the lens is an optical instrument. We have 1 over F is equals to 1 over U plus 1 over V, where F, of course, is the focal length of the lens, U is the object distance, V is the image distance. So from here you can make, if you are given, for example, you are given the focal length of the lens, you have the object distance, you can easily find the image distance. If you are given the image distance and the focal length, you find what? The object distance. We also look at the power of the lens. Remember, the lens is an optical instrument. It is from this lens that we are able to make medicated glasses. Depending on your type of eye problem, you could use a convex lens, you could use a concave, you could use a plano-concave or biconvex, depending on what the constructor or optician wants from the lens. So we look at the power of the lens. The power of the lens determines how much defect you have and how to correct it. So the power of a lens is the reciprocal of the focal length, given as power of the lens is equal to 1 over F. What's the SI unit? It is measured in diopters. So you see some lens, once the optician is done, after testing you, gives you a lens, you see a prescription plus 1, plus 2, plus 1.5 or minus, depending on the situation that you have. Okay, so from there, we'll take one or two calculations involving the lens formula and the power of the lens. So let's take one on the lens formula, and then we'll take one on the power of the lens. So it is placed at a distance of 75 centimeters from a converging lens of focal length 30 cm. Remember, we said object is placed at a distance of, so we are looking at object distance, which is what? 75 cm in front of a converging lens of focal length. F is 30 cm. We are looking at the image distance, V. What do? We say the reciprocal of the focal length is equal to 1 over the object distance plus 1 over the image distance. In this instance, you are looking at the image distance. So you make it the subject of the formula. You have 1 over V is equal to 1 over F minus 1 over U. So we have 1 over F. F is 30 cm. U is 75 cm. If you find the LCM of the two, I would like to break it down so that I have something less. We have 1 over 6 minus 1 over 15. So the LCM, we can use 30. We can say the LCM is 30. 6 there will give us 5. 15 there will give us 2. That will be 3 over 30 equals 1 over 10. But remember, it is the reciprocal of the focal length. So to get the reciprocal of the image distance. To get the image distance, we take reciprocals on both sides. That will give us 10 cm. From here, you can also determine the position of the image. Remember, object distance is 75 cm. Image distance you have found to be what? 10 cm. So it means that if you place the object beyond 2f, the image will be formed somewhere here. Also look at the sign. We have plus 10. Remember, we say the signs that come with these distances is very important. So we have plus 10, meaning that this object, this image is not inverted like the other images. It is erect. It is between the pole and the principal focus. I hope that is clear. I will take the object distance 75, focal length 30. You are looking for the image distance. The length equation is 1 over f is 1 over u plus 1 over v. We make 1 over v the subject of the formula and then substitute. We got 10 cm as the image distance. Let's take one problem on. Okay, so supposing you have, in this particular question now, you have the focal length as 30 cm. What will be the power of the lens? The power will simply be the what? The inverse of the focal length. So in this case, since the focal length is 30 cm, we have 1 over 30. That will give us 0.33 diopters. What are the applications of these lenses? As we said earlier, the applications: 1, the human eye has been created in such a way that it has a lens in it. This lens is what helps us view objects. It magnifies, it diminishes depending on the object distance. We also have other applications like the telescope that we use, the microscopes, the other astronomical instruments that we find around us. Even the cameras that we use to take pictures have lenses in them. Be they your phone cameras or whatever, they have lenses in them, and all the lenses work on these principles. From there you can also find the focal length of the lens, you can find the power of the lens, you can find the magnification, and so on. Okay, so in summary, first we say what is a lens? It's an optical instrument that refracts light. 2, there are different types of lenses. We have 2 in particular, the convex lens and the concave lens. We say the concave lens diverges rays of light. The convex lens converges what? Rays of light. The convex lens converges rays of light. Now, we also say that For the concave lens, for each object distance, you will get the same image characteristics. However, for the convex lens, depending on the position of the object, if you place the object at the principal focus, you get different image characteristics. If you place it at 2 times the principal focus, you get different image characteristics. We illustrated where we place the object beyond F, the principal focus, and we got what? An inverted magnified image of the object. We have also looked at the lens formula 1 over F is equals to 1 over U plus 1 over V. We have taken an example on that where we got this. The calculation shows us that the image is diminished. It is not magnified, it is diminished, it is erect. I have also talked about the power of the lens. It is the reciprocal of the focal length. Unit is what? The diopter. We have also taken an example on that. I expect that you go back and then you look at more examples on the lens formula, the power of the lens. You also try to construct those images giving different object distances. I'm going to list the object distances for you to try at home. 1. Place the object at F, the principal focus. 2. Place the object between the pole of the lens and the principal focus. 3. Place the object beyond 2F, twice the principal focus, and then investigate the characteristics of the image and see what you get.